Hello, this video is about our AUTOML 2024 conference paper, Training and Cross-Validating Machine Learning Pipelines with Limited Memory. Cross-validation is important for automated machine learning because it reduces overfitting. To do this right, we want to train or cross-validate the entire machine learning pipeline. The problem is that, unfortunately, that is challenging when memory is limited. This paper proposes a solution based on monoids. A monoid is simply a set with a binary associative combine operation, and we define a monoidal operator as a machine learning operator whose learned coefficients are a monoid. That means we can combine learned coefficients from different batches, which helps reduce spilling. And furthermore, we can combine learned coefficients from different folds, which helps reduce computation in cross-validation. Let me illustrate a monoidal operator, specifically a monoidal simple imputer that uses mean for imputation. In this example, we have 3 input batches, and let's assume there's only one column. And in these input batches, the missing values are denoted with the bottom symbol. So the first batch, D0, for instance, has a missing value in the middle. When we compute the learned coefficients for the first batch, we sum up how many non-missing values there are and what their total is. So there are 2 non-missing values that together make 5. We can do the same thing for the second batch and for the third batch. And now we have learned coefficients separately and independently for each batch. We can combine these learned coefficients by simply adding them together. And for different operators, you might use a different monoidal combine operation. But in this case, there's a total of 6 non-missing values in the entire dataset, and their sum is 18. Once we have the learned coefficients for the entire dataset, we can use the simple imputer to transform each batch independently. So for instance, in the first batch, the missing value gets imputed as 3, which is 18 divided by 6. So it is the mean of the non-missing values. And similarly, the second batch does not have any missing values, and in the third batch, we can impute both missing values as 3. And now that we have transformed the data, we can use it further downstream in additional operators of the same pipeline. Now, one thing that we were very happy to notice was that you can actually express a pretty comprehensive set of operators as monoids. So other monoidal operators that we have implemented include min-max scalar, standard scalar, projection, different flavors of encoders, one-hot ordinal, target, and hashing encoder. You can even do feature selection. And it's not even limited to preprocessing operators. You can also write a classifier by creating a monoidal ensemble. Now that we have defined monoidal operators, we can use them for an entire pipeline. So let's look at a batched training regime that uses the full transform approach. And in this example, there's a pipeline that has 3 operators, A, B, and C. We first fully train A by combining the learned coefficients from all batches. Then we transform the input data using this operator A. Then we fully train operator B on each batch separately. Then we transform the input data on B. And finally, we train operator C, and we don't need to transform the input data if all we are interested in is the final learned coefficients. Now, this batched training full transfer regime has desirable properties. First of all, there's some scheduling flexibility in which order you can execute these tasks in the task graph. And one of the schedules is actually equivalent to just using scikit-learn's partial fit, but we are not limited to that schedule. We can also use any of the other schedules, and they will also yield the same learned coefficients as scikit-learn. And then, of course, the desirable property is that you can run everything in big O of max fan-in memory. And so here, fan-in is the number of inputs to each operator in the pipeline. And this turns out to then let us run in limited memory. We also have empirical evidence for this. So what we did here is we ran 4 large data sets, both in our batch training full transfer regime and in scikit-learn. And when we provide enough memory so that both our regime and scikit-learn succeed, then they yield equivalent results. On the other hand, when we limited the memory such that scikit-learn runs out of memory, it turns out our batch training regime does not run out of memory. It still succeeds and yields the same learned coefficients. One other remark is that this works with any monoidal machine learning operator. Another regime that is enabled by monoidal machine learning operators is the batch training partial transform regime. In this regime, we transform a batch with an operator even before that operator is fully trained. All that we require is that the operator is trained up to and including the batch that we are trying to transform. This has a new desirable formal guarantee, which is you can actually train the entire pipeline, so all operators in the pipeline, up to a certain batch I, before you even have to scan the next batch I+1. So for instance, you can use this for early stopping or for learning curves or things like that. On the other hand, this regime loses a formal guarantee from the previous regime, from the full transform regime. We are now no longer guaranteed to get the same results as scikit-learn's partial fit. However, we can empirically evaluate how similar the results are. So we did an experiment where all the pre-processing operators are monoidal, and where the final estimator, while not monoidal, supports scikit-learn's partial fit function. So MLP classifier, LightGBM classifier, etc., etc. They all have a partial fit. And the results from this experiment are that the green bar and the red bar, which are the full transform regime and the partial transform regime, are basically the same. So empirically, even though we don't have a guarantee of same results, we do see the same accuracy with these two bars. On the other hand, some of scikit-learn's operators, so for instance, in particular MLP classifier, they don't get the same accuracy when you run with partial fit as opposed to when you run with full fit. Another limitation of the partial transform regime is that it requires operators to not just be monoidal, but also convergent. Monoidal machine learning operators also enable cross-validation with an in-fold regime. By in-fold, I mean that there's no communication across folds while training each variant of the pipeline. This has the formal guarantee that it saves a factor of k-1 two monoid tasks for source operators. In the example, A is a source operator, and we can see there's only one two monoid task for each fold, whereas for the operators B and C, there are multiple two monoid tasks for each fold. Another nice guarantee of this regime is that it yields the exact same results as scikit-learn's cross-val score. I'm going to defer empirical results to the next slide. For now, I will just observe that the cross-validation in-fold regime works with any monoidal operators. Finally, let's look at cross-validation with an out-of-fold regime. Out-of-fold here means that we transform each fold using an operator trained by all the other folds except for that one. This regime has the guarantee that it saves a factor of k-1 two monoid tasks, not just for the source operators, in this example A, but also for all other operators in the pipeline, in this example B and C. On the other hand, it lacks the formal guarantee of the in-fold regime, and it might have different results from scikit-learn's cross-val score. We compared the two regimes empirically, and as expected, the in-fold regime, denoted INF, is slower than the out-of-fold regime because it saves fewer tasks. On the other hand, if you use the ranking capability as a measure of overfitting, the results are a bit murky because of the large error bars, but it seems like the in-fold regime overfits slightly less. Another drawback of the out-of-fold regime is that it requires convergent operators. To conclude, in this talk you saw monoidal machine learning operators and how to use them for batched pipeline training, as well as for pipeline cross-validation, and monoids enable reuse there. The paper, in addition to the things you saw in the talk, also shows you a relational algebra intermediate layer, and then that relational algebra enables us to implement all of our monoidal operators on two different backends, pandas and SparkSQL. Besides monoids for operators, we actually also have monoidal metric implementations. And finally, I showed you in this talk cross-validation in a non-batch setting, but you can actually batch the cross-validation as well. And finally, our open source implementation is part of the LALE package, and it includes everything in the talk and in the paper, and everything is exposed via scikit-learn compatible APIs.